Thank you for joining our seminar today, How to Ensure Your Blackburst Survives the Introduction of PTP. My name is Cindy Zulsdorf, and I'd like to introduce Steve Holmes, Video Applications Engineer for Leader Instruments based in Los Angeles, California.
How's everybody doing? Glad you're joining us this morning.
Glad you are here. And Kevin Salvage, Sales Engineering Manager for Leader Europe, based in London, United Kingdom.
Good afternoon, everybody who's in Europe, or good evening if you're a little bit further east.
Yes.
All right, well, we've all grown up with Blackburst reference center facilities, right? And the only change we might have had to manage is the introduction of tri-level sync when facilities started migrating to HD. Now, expansion of Blackburst tri-level sync reference systems were relatively simple. Either daisy chain the new device with the loop-through genlock output from an existing device, right? Or use a distribution amplifier to split the BBTTL reference signal. What could be simpler? Now, broadcasters are faced with a new reference precision time protocol, or PTP as we call it. Fortunately, this reference is already being used in other industries like finance, power utilities, telecommunications, and has standards associated with it. Now, every industry sector claims to be unique, and the broadcast industry is no exception. However, for PTP, we very much are unique. The standards authorities have created a broadcast-specific profile for PTP, and understanding how that profile is applied to the new broadcast industry will ensure that your existing SDI infrastructure can integrate with your new video over IP infrastructure without QoS issues being introduced. Steve and Kevin have been involved in a number of video over IP deployments globally. So what better way to ensure that your video over IP PTP reference and existing Blackburst reference can coexist than to join Steve and Kevin right now as they highlight some of the pitfalls they've experienced. We are going to be taking questions all through the seminar. So please use the chat and send us your questions. Now I'll turn it over to Steve and Kevin.
Thank you very much, Cindy.
Thank you, Cindy.
So, Steve, we've been involved in a number of projects with our customers. And should we start with by reminding everybody what Black and Burst is and where it comes from?
Certainly. So, everybody should be moderately familiar with a conventional system where we've got a primary generator, a backup SPG, like our 4610s here, that feed off to a ECO, and we take the analog Blackburst, our tri-level sync, or HD SDI, and all of then that goes out to a set of typically distribution amplifiers that will distribute the house bars, the house reference, to the rest of the network.
So, we've got that. We've had that for years. That's worked well. What is PTP, or to give it its proper title, Precision Time Protocol?
PTP essentially is the Blackburst or tri-level for uncompressed IP video networks. It's a IP protocol that is used to synchronize the clocks throughout an IP network. And as you mentioned earlier, it is based on an established standard that points to a point in time where, if you will, the Big Bang happened for PTP, which we call the epoch. And the epoch just happens to be 1970, January 1st of 01. So its time starts there. And then we count out in nanoseconds from that point forward. So it's a very, very precise time. And we are going to use that instead of a pulse that we use in Blackburst or tri-level. we're actually going to use time, and we're going to put timestamps on things, and so that things happen with that precision clock at particular points in time. Now, SMPTE has added some things to the IEEE 1588, which is the international standard for PTP, because there was nothing in there that referenced video. So one of the things that we need to do as a video industry is make sure that our devices that we use are aware of the 2059 standard that SMPTE used, so we don't lose that part of the standard. Because right now you might not be using it, but there may be some devices that you add to your network that will want that piece. And then there is the way that we use the PTP to deal with a primary clock, which we call the Grandmaster, and a leader clock, which is a standby, like our primary and our backup SPGs that we use going into an ECO, but this is done completely differently. So the things that SMPTE added, or some things that PTP would have no idea of, you know, things for analog high definition, digital high definition, some things about AES audio and time code generation and the SMPTE 309 date. So none of that would be in the standard 1588 that we dealt with. So those are the pieces that could get lost if you don't have a PTP aware network that knows about the 2059 standard. So -2 just added some other things and did some refinements on other pieces so that we could take things that were in 1588 and say, this is how these will be used within the video network.
We've talked about this being used by other industries, but what's the difference between NTP and PTP? And could NTP be a sync source? It's time-based. And could it be used as a lock source for PTP?
Great question, Kev. No. One of the unique things about NTP is driven by software. And anything that's driven by software could be interrupted by things when you have a service that is requesting something and you have to pause that part of the application to go do another process. So the other thing is NTP only provides millisecond accuracy. The PTP provides sub-microsecond accuracy to the end device so that we have pixel accuracy. And it's set up so that we directly drive it off of GPS versus locking onto a NTP server that may be locked onto another server that eventually hits some form of grand clock source. So the Grandmaster within a PTP network pushes time to the receiver or the followers, the received clocks. NTP is you have to go request that, and it's a polled request, and it doesn't happen that often. So it just doesn't have the accuracy or the stability that we need.
Right. So hopefully that's cleared up that question that we're frequently asked. So how do we implement a PTP timing reference system within our existing SDI-based facility?
So most people start off with kind of a isolated network, if you will, because one of the best things you can do is set up a little island, a green field, where you can set it up and learn exactly how it works. So if you're adding this to an existing network, you can lock your PTP generator to your existing house black. Now, it's a good way to learn how things are going, but it's not the best choice for long term. For long term, because the clock reference off of house black is not nearly as accurate as your house reference if you were to come in off of GPS. So GPS is going to give you the best clock, and then your PTP sync generator here, like the LT4610, now can be your source for your black burst, tri-level, your test signals, and now your PTP and your black burst are all coming off the same clock, and your entire network, be it SDI or IP, are completely locked to one another.
Let's get into a bit more detail. So how does this PTP thing work?
Before we kind of get into how it works too much, let's cover a couple basic terms. So within PTP, since it is a clock, there is a hierarchy to these clocks. So the clock that your entire system is referenced off of is called the Grand Master. It is the ultimate clock source for everything else within your IP domain. A leader clock is a clock that is either synchronized to the Grand Master or is synchronized to GPS, but is not online. It's not the Grand Master at this point in time, but it's waiting that if the Grand Master falters, it will take over. A receiver, they're calling the receiver a follower clock. Now, these names, you may have heard some other names for all of these. They've gone through and changed the names of what we're calling the clocks now. So an ordinary clock or follower is your receiver, and it's following what the Grand Master is putting out as far as time. There's also a PTP domain that is a logical grouping. All it is just a grouping of PTP devices. So if you happen to have a video PTP source, you can put it on a specific domain. If you have a AES67 PTP source, you could put it on its own domain. Dante uses PTP. It's going to be on its own domain. So domains can be all on the same network, but different domain numbers, so that they separate each other.
You alluded to it earlier, and I've heard consultants say there isn't such a thing as an emergency changeover unit when it comes to PTP sources. Is that correct? How do they work? How do they know who's the Grand Master?
You are absolutely correct, Kevin. There is no ECO per se in a PTP network. The Grandmaster and the leader that is set up to be the next in line communicate with each other through the network. And it is sending messages in both directions, and the Grandmaster to the follower clocks, and the clocks that would be your backup are listening to those messages. And there is a voting that takes place that sets up who is going to be the Grandmaster, and then when something happens, the other clock is going to walk into it. So the other thing that is unique about PTP is it has a method within it to compensate for the delays in the network so that the end time will be exactly what the time is in the Grandmaster. It measures the network delay and subtracts the network delay in the follower so that the follower's time is as close as we can get it to exactly what the Grandmaster's time. And that way we have accurately aligned time.
Let's have a look at how this is kind of implemented, you said already that it can coexist inside a sync pulse generator that we're used to for Black and Burst, tri-level sync, our audio and SDI. Does this just simply bolt on top?
Basically, yes. So we looked at the conventional primary SPG, backup SPG, all going to an ECO, and then the voting or the decision of who's online is controlled by that ECO, and both units are always putting out their signals to the ECO, and then the ECO is normally on your primary and putting that out to the distribution amps. If it falters, it switches over. In PTP, the signal comes directly via IP out of that sync pulse generator to the network. So your primary generator is going to be outputting PTP. Your secondary generator, after the voting takes place, will be listening to the primary generator, but it will be also directly attached to the network and ready to go at a moment's notice if something falters in the primary. So what you end up having is your two SPGs directly linked into your 2110 network, and they're communicating with each other via that 2110 network. You will also have here the analog or the audio and the video and all your sync signals going over to your ECO, and then that will go out to your network for all of your SDI and Black and Burst needs that you have. So this way, the two SPGs are synced to PPS and are exactly the same. And then we have the ECO that's going to put out their signal, but we're going to go out to the network, come back on the network, and have some communication between these two units. So if we kind of look at it from just a very simplistic picture, we've got two sync generators, two SPGs that are outputting PTP on a 2110 network. When they power up, they start listening and they will send announce messages saying what their status is, what their lock is, several pieces about this, and the two generators will talk to each other. Then this voting will come up that we call a BMCA, Best Master Clock Algorithm, and it will then decide, because both units will run that BMCA, and via that BMCA, one of the units will say, hey, this piece of me is a better option than your piece. It's typically a priority where the lowest number wins, and the one unit that you want to be your primary clock will become the grandmaster. The secondary clock will be the clock in waiting, will be the leader that will be there if the grandmaster happens to falter. So there's a few things that happen with this BMCA that happens on here. We have the grandmaster and the leader will have all of these pieces here. So we've got some pieces here. Priority 1, it's a numeric value that is used in the voting to determine who the grandmaster will be. And it's a number between 0 and 127. Both of the two generators should have the exact same priority 1. So that's going to set them on the same voting plane. Then the next thing down here is the clock class, clock accuracy, and the clock variance, which is basically how good is your PTP lock, or are you locked to PTP? So this is going to be the quality of the clock that you are locked to. And then we have priority 2. And priority 2 is what you're going to use if both units have the same priority 1, you're both locked to GPS, have the best clock you can get off GPS, then we're going to use priority 2 to set up the hierarchy. Who's going to be the grandmaster? Who's going to be the leader coming in for number 2? Who's going to be the leader coming in for number 3, number 4? You can have as many units, sync pulse generators, stacked up. And then if someone doesn't set that up and you set both priority 1 and priority 2 exactly the same, well, there's got to be something that's going to break that tie. So the MAC address is the tiebreaker, but that puts who's going to be your grandmaster out of your control. It's going to be who's got the lowest MAC address. And you really want to set up priority 2 so that you are absolutely in control with this. So you have the ability within your sync pulse generator to set what domain it's going to be on. That's going to be that logical grouping of all of your PTP sources. But then you can also set a number, and it's just an arbitrary number that you say, okay, my priority 1s for all of my sync pulse generators are going to be, in this case, 12. My secondary, in this case, for priority 2 is going to be 12. And then what you'd do is you'd set, like 14, 16, 18 for the other priority 2s, for the other generators that will fall in suit behind this unit if this unit happens to falter.
This is where we have to put some thought into how our architecture is going to be designed, the failover and that. But you mentioned there's a piece in there that we sort of don't have any, well, we do have, but don't have control over, and that's the clock class. You've got a bit more detail on that, because, that can have a big impact on the system and the hierarchy, how it cascades when it falls over.
So the clock class, like I said, is the quality of the clock, and it's really based on what you are locked to. And in the case of a GPS locked device, the best clock class you can have is clock class 6, which means that you are either GPS locked or you are locked to PTP, which is GPS locked. So it becomes the best that you can get. If you are a clock class 0, that means you are the atomic clock sitting in Boulder, Colorado. It is the absolute source of time. So after the satellites and we come back down off the satellites, we can be clock class 6, and our time of day off of that epoch is absolutely perfectly locked. If we lose lock and you go onto the internal oscillator will maintain time, but we can't be clock class 6 anymore. So what we drop to is clock class 7, saying, yes, we had solid lock, my time is set to the epoch, my internal oscillator is stable enough to hold that time for a given period. So once that time has elapsed, based on the quality of your internal oscillator, which is an oven-controlled oscillator, you will drop down to 248, just saying, I'm on internal oscillator now, my epoch time, I can't absolutely tell you where it is because it's been so long since I was last locked to GPS. So it ends up going to 248, just saying, hey, I'm on an internal oscillator. The oscillator is dead accurate, but we just don't have the epoch time to be absolutely perfect. If you lock off of black or tri-level, you will be clock class 220, saying that, yes, I am not GPS, I am locked to a stable clock, but you can see how far, and that's why I was saying it's best to lock your network to GPS once you get into putting in your PTP more into your source so that you have a much more stable and accurate clock. So we have the ability to look at all of these parameters within our waveform monitors. So with a PTP aware waveform monitor getting into the IP, we've added things so that we can look at the domain that is being sent to us, because we have to be on that domain. So we can look at the PTP messages that are coming into us and extract, okay, domain 44 is what's being sent to me. Then we can look at, yes, we are locked, or we are set for domain 44. And we happen to have my priority 1, which in this case was 12. We can see that my clock class was 6, so I am 100% GPS locked. And I am sitting here with priority 2 as 12. Now what you're seeing here is on the left and the right, just the 2 ports that are coming in, and we'll get into why there is 2 ports coming in a little later discussion. And then you can see here that my time source, because I am clock class 6, we're just putting a message in here. Yes, you are locked to GPS. Now, if for some reason all of these values on the bottom don't fill in, the chances are what you have set the follower, i.e. the waveform monitor in this case, the receiver, you probably do not have it set for the correct domain. So it's got to be set to that value that you are receiving.
Shall we see if everybody's been paying attention? Shall we put a poll out and let's put up a typical system setup with the information that Steve's been speaking about, and we're going to ask you the question. Using the best master clock algorithm, which device is the Grandmaster?
So on the right-hand side, we have our clock priority 1 at 14, priority 2 at 20. On the left, we have our priority 1 at 14, priority 2 at 26. They're both clock class 6. You should have the poll question in front of you and tell us which one you think, the red network or the blue network, is the Grandmaster. We'll give you just a second here to click on that. Okay, Kristen, why don't you put up the results from what we've got here? Let's see what people say. And the majority of you are absolutely correct. The network on the right, the red network, is the Grandmaster because its priority 2 is lower than the priority 2 on the blue network. They both have the same priority 1, same clock class, so it gets down to the voting of that priority 2, and the BMCA says that the unit on the right will be our Grandmaster. Let's take a look at this in a slightly different light here. This case, again, on the right, we got priority 1 of 12, priority 2 of 20, and on the left here, we have my priority 1 of 12 and priority 2 of 26. So the unit definitely on the right is my Grandmaster based on that. But if I take a hit in my GPS and I have a degraded GPS signal, who is the Grandmaster now, based on just taking a hit in my GPS on the unit on the right? Take a second. Let's see what we think. Let's see what people said here. Absolutely correct, folks. The unit on the left, the blue unit, is now the Grandmaster because the clock class sits between priority 1 and priority 2, and it's going to be the determining factor. It overrides priority 2 because it's above priority 2. So since the unit on the right went to clock class 7, the unit on the left has clock class 6, it's going to take over and become the Grand Master. So that's how this BMCA works. It's a tiered voting system. So the unit, like I said, on the left is the Grand Master in this case. The same thing would happen if we completely lost GPS, or if GPS was actually cut, we would still have the same situation that the unit on the left would be the Grand Master under all of those circumstances. But now things have changed a little bit. I still have my priority 2 at 20 on the right, my priority 2 at 26 on the left, on my blue network. The unit definitely on the right is the Grand Master based on these. If I lose GPS right now, who is the Grand Master in this situation? Have a little fun here and take another little poll and see what everybody says. What is our outcome? What do people say is the Grand Master? Oh, a little undecided in this one. Yeah, we're almost a 50-50 split between where we are on this. And this one gets a little unique, and I can understand the reason for that. Well, the unit that is our Grand Master is still the unit on the right, even though he's got a screwed up GPS signal. The reason for that is, look at the priority 1 numbers. The unit on the right is priority 1 of 12. The unit on the left is priority 1 of 13. Since priority 1 is the highest voting and it's above the clock class, so even though the clock class dropped to 7, which was a holdover, it still says, I am the unit you are going to stay locked to. And this is why what I was talking about earlier, that you need to make the clock classes at priority 1, the priority 1s exactly the same. Otherwise, you will not switch to your backup on a loss of GPS. Now, you will switch to the backup in the case of the signal going away. Now the unit on the left will become the Grand Master because there is nobody else. He no longer sees that priority 1 of 12 on the right. But on a loss of just GPS and a reduced quality clock, the unit on the right is still going to stay that Grand Master. So this is one of the reasons why when you build out your network and you get to SPGs running and you have them tied in, you need to test your failover BMCA not only by yanking the PTP off of the switch, but you also need to make it fail over by taking off the GPS signal, because they're 2 different things. One is a complete absence of PTP. The one with the GPS is just going from clock class 6 to clock class 7, where the unit on the left is still clock class 6, and it should fail over to that unit. So there's some little tricks, and I can't tell you how many places I've been that they do this, and you walk around the back, just yank off the GPS, and it stays on the unit, and everybody gets flustered and can't understand why BMCA is broken. And it's really not. It was just you didn't configure the network exactly how you should have.
Thanks for that, Steve. So, you touched on domains, and I've heard people say there are certain domain numbers that you should avoid. Are you able to enlighten us about this?
I am. Yes, there's really 2 domains that you really want to kind of stay away from when you set your network up. The default domain is 127, and that can cause issues. The other domain is domain 0, and domain 0 is used by audio services. And typically, you aren't going to have two things on the same domain. So if you ever put in a AES system or Dante or anybody else, they typically will run on domain 0. So you want to leave domain 0 open for any of that in case you are on the same network topology and you're running your audio network along with your video network, which is perfectly fine to do. You don't want to leave it on 127 because that's the default. Every device that's added to your network that may have the potential of being a grandmaster is going to come in with that domain value. If their priority 1 now happens to be lower than the priority 1 you chose, they will take over the network. So you don't want a new device that's added to your network to be a rogue and somehow take over your network. So you want to be in control of that and change it to some just other value. Doesn't matter what the value is. I run 44 for my domain in my office lab. And so it just, anything else that I put on my network isn't going to take over because there's chances are astronomical that it's going to be set to 44 when I turn around and do this.
So we've talked about the best master lock algorithm and how it's providing you with a level of resilience. Obviously, lots of our customers in their 2110 environments have employed 2022-7 to give them that seamless switching. How does PTP kind of handle when it's in that configuration, Steve?
In a -7 network, a 2022-7 network, what you will have is two complete independent networks that have the same data on them, and they will be coming down to the follower, the receiver. You need to have a connection between those two networks, even though you want them to be 100% air-gapped networks as far as your video, audio, enhanced data is concerned. There needs to be a PTP connection between those two networks. So the BMCA between the two SPG generators will take place. And what will happen is, in this case, the generator on my Amber network happens to be the grandmaster because of its priority 2. So its PTP will go across that link, and both the Amber and the Blue will have the same PTP source coming down to the follower. And that way you have complete failover that you are getting your PTP and you're getting the same PTP on my Amber network as I'm getting on my Blue network. There's many different ways to do this interconnection between the two, and that gets into doing your network topology, and you may not want to do it at the network level. You may want to actually move it up and do it closer to the sync generators. But that just gets into how you do your individual topology. The 2022-7 is a one-for-one packet replacement. So you're going to have a sender, you're going to have a source that is a single source. It's going to go into, or it's going to have a twin output. It's going to have a stream A and a stream B on two different IP addresses, two different multicasts, but with exactly the same data. And you're going to go through your two networks into the receiver. And in the receiver, there is a packet picker. And that packet picker is going to be looking at the data. And in some cases, depending on how they design the packet picker, it may just ride on one side and take all that data until there is a fault and then grab the data from the other side. Some of them, first packet in is who's going to go out. And it really doesn't matter whether you grab the packet from the red or the blue side in this case. But, so let's just say we're grabbing all the data from the red network at this moment. And all of a sudden we take a hit in the red network and I lose these two packets. the packet picker is just going to grab those two packets from the other network, and there's not even a hit in the network. Your receiver sees good data, and you're absolutely 100% covered for that fault that happened in the red network. Now, this does lead back to you need to periodically monitor these two networks, because since the 2022-7 did this seamlessly in the background, you may not even know your red network is in trouble. So you do have to monitor your networks to verify that they're both functioning correctly.
As we've been going through this, we've been using terminology that basically is a new language. Unless you're from the telco world, you're an IP network engineer. Are you able to quickly summarize some of these terms, for our audience, so that I understand exactly what we're talking about here?
Certainly. So we've already talked about the grandmaster, the ultimate clock, and then you have your leader clock that will be the second clock, waiting based on priority to take over. The follower happens to be the receiver. Anything that's receiving the PTP information and using that as sync is a follower. Then we have the PTP aware switch we talked about. Again, the 2059 protocol. So we want that switch to not exclude those packets. So they're extensions to the management messages that are going on. And we want those to be going through. Then we get into this little thing that is a boundary clock. And a boundary clock is kind of unique in that it is a follower from the north, i.e. from the sync generator coming to it. It becomes a follower of that sync generator, but it becomes a leader for all of the devices below it. And it's kind of a separation between what's happening with the PTP generator and what's happening below it. And the reason for this is to limit the PTP traffic going back to the grandmaster. So PTP is very verbose, and if you put too many followers on a network, you can actually have PTP congestion, and you start dropping the messages. So this allows you to have a much wider network, and the boundary clock then will become the sync source for everybody below it, and those boundary clocks are all locked to the clock above it. A transparent clock is a clock that adds, it looks at the PTP timestamp coming in, and it looks at the PTP timestamp that's going to be going out, and it puts in a correction factor in the PTP message that says, here's my input was this time, my output was this time, so it spent this much time inside of me. It's a correction number.
If I understand this, and I'm going to use black and burst terminology because that's how our industry typically works. It takes something that we know, we've worked with for years, puts a new technology on top of it, proves it works, then starts to see the benefits of it. Would you describe a transparent clock as like a fan out, providing a loop through input and multiple non-reclocking outputs, and the boundary clock as being an equalized stroke reclocked output, providing regeneration signal on multiple outputs? Is that too simplistic to describe them?
It's a little simplistic. It's really, really close. A transparent clock, though, does do some things where a normal fan-out DA just gives you the same signal. The transparent clock does give you that fan-out, but it gives you that correction field for the amount of time that it took for the PTP message to get through the switch. The boundary clock is, to a degree, like a reclocking DA, other than there is a separation on northbound, southbound. It is a receiver, like a reclocking DA would be on its input, but it is a brand new PTP source on the outbound. So there's akin to the reclock piece on that, but that's about as close of an example as you can make. So we looked at all of these pieces here, looking at a grandmaster, a leader, boundary clocks, transparent clocks, and a follower. If we kind of look at this in just a real simple line drawing here, we've got the PTP generator outputting PTP messages, in this case, into a transparent clock. The messages will go through that transparent clock, and they will get that correction field added to it, so you know how much time that you need to modify for. And if you notice on the second PTP generator, it's not generating PTP. It's just listening to what's going on and looking at those announce messages and making sure everybody's doing what they should. Down on the bottom, we do have a boundary clock. The boundary clock is going to be a follower from the northbound traffic, but it is going to be a generator of PTP southbound to everything that is plugged into it on the receive side, and it recreates brand new, so any of these PTP messages don't go beyond that switch. So the switch will have PTP messages going up to the grandmaster, but my switcher, my camera, another PTP generator as a follower will not have direct messages back to the grandmaster, but they will be locked to the grandmaster's exact time.
Data centers traditionally use like a 3-tier topology, but broadcasters prefer the leaf and spine topologies. Does the network topology affect the PTP architecture?
It does. A typical data center type topology might look something like this, where you've got layered switches and you've got multiple interconnections for route tables, where if something's congested, the access layer actually could go all the way up to the core layer if it had to, or to a distribution layer. And just based on traffic, it can take different routes. We can't have that happen in a PTP network. A PTP network, the transmit direction and the receive direction must be the same path. PTP is based on a symmetrical network. You don't want a delay in one direction from a switch to be greater than a delay in the other direction. Also, the leaf spine that you talked about is much easier to manage if you need to grow your network. So in this case, we've got our red and the blue networks here. They're going into a switch to distribute PTP to both networks. And also that switch now allows you to grab PTP if you have other devices that just need PTP sync. But now the rest of those networks are 100% air gap from each other. And the path to get from one device to another device is only boundary clock, spine, boundary clock. It never goes beyond that, no matter where you happen to be going. So it works very nicely from that standpoint. Some people may want separate distributions for their PTP. So you could put into conventional switches for the PTP messages and then make a PTP only pipe between those two switches so that the BMCA can take place. Or you could do this at the spine level. I like doing it above the spine level because if something happens to your network, you aren't relying on that network, the spine, to convey the PTP messages across. If you need more bandwidth, all you have to do is add more spines, and the traffic is still boundary clock or leaf to spine back to leaf, no matter where you're going, but it just increases your network bandwidth. If you need more followers, more nodes, you just add more boundary clocks, more leafs. And the leafs then connect to the existing spines that you have. So it's very easy to grow these types of networks.
Earlier on, you mentioned that we sort of know PTP can calculate sort of like the propagation delay through the switches and networks. How does it do that? How does it know how long it takes for a signal to travel across the system?
Okay, well, that is part of the BMCA part of the announce messages, the sync messages, and delay requests and delay responses. So we have an announce message. It basically says who you are, what your priority 1, priority 2, your clock class is, and that is sent out to the whole world. Then we have a sync message. The sync message is the grandmaster's time to the network. Now, all of the followers, the receivers, will now send back a delay request, which is their time going back to the grandmaster. The grandmaster then will again respond with his time back to the follower. So it's kind of this sync. Now the follower knows what the grandmaster's time is. So the follower now has T1, which is the grandmaster's time. He's got T2, which is his own time. He's going to send that at T3 at some other point in time back to the grandmaster. So now the grandmaster knows what the follower's time is, and he knows what his own time is. And then he's going to send a delay response, which again is his time, and the receiver will now have what the original time was, what his time was, what the time was when the follower sent his time back to the grandmaster, and the grandmaster's new time on the response. And if you really take T2 minus T1, that gives me that delay time. And if you take T4 minus T3, it gives me the delay time going back. So T2 minus T1 is the delay of the grandmaster's time to the follower. The T4 minus T3 is now the follower's delay time that it took to get back to the grandmaster. So you take those two pieces, add them together, divide it by 2, and now you've got a 2-to-1 of the delay going forward, the delay coming backwards. That's why it's so important to have a network that is symmetrical. And the follower will take those T1 times, and that's what he's going to use to pull himself in. Now, he isn't going to instantaneously just pop to T1 time because it's a clock. It's got a phase lock loop in there. And you also don't want to shock your network, and all of a sudden, so if you lost GPS and now you're getting GPS back, it's going to walk slowly back into that time so that your network doesn't do like some of our old black burst networks used to do, like a 360 whirl when we go through all of that. So the waveform monitors will give you that T2 minus T1 time, the T4 minus T3 time. And so you can see that the two numbers there on the left are very similar to each other, saying the delay through the network is symmetrical and very, very nice in this case.
We've got there a screenshot from obviously one of the leader waveform monitors. Do we have that in a bit more detail? Because obviously that's looking at it in isolation. You've mentioned about delay time and offset times. Are those graphs visible to us as well?
Yes, they are. The delay time and everything that's happening. So at the very top, we're going to tell you what grandmaster you're locked to on both ports. So it is the MAC address of the grandmaster that we are locked to. We can see the messaging coming in on port 1, port 2 from the PTP generator. And we can see the domain that is being sent. And we can get a graph of that delay time. in 1 second buckets. So this is the amount of delay min and max within a 1 second bucket. And then you see those buckets move across, and you can see the graph of those buckets. On the right over here, you can actually see now that T2 minus T1, the min, max, and current. And if I zoom in just a little bit here, you can see that the time is not absolutely symmetrical. So in this case, the T2 minus T1 time is a little bit larger than the T4 minus T3 time. And you want to be careful about that, because that means that the video network is being stressed that it's taking more time to get from the PTP generator to the follower than it is from the follower back to the PTP generator. The messages from the PTP generator to the follower are going with all the traffic. So this suggests to me that the switch architecture that I am currently going through, if this stays like this and gets bigger and bigger, that network is starting to get congested. And you need to start looking at, maybe I need more bandwidth in my network, that it's starting to slow down my PTP messages. And then you can see all of the message rates, how many times a second each one of these messages are actually being sent. Here we can see, the event messages, the general messages, and who is in which one of these particular messages.
So, Steve, we hear a lot about quality of service settings on switches. Can we use the QoS for SMPTE 2110 and PTP?
That's a great question, Kevin. We can for parts of it. You don't want to use QoS for the video or for the audio, because they are the main flows, and every packet then would be tried to be as the best packet possible. QoS needs to be set so only a specific flow that isn't necessarily the main flow through the switch would have the QoS on it. If you were to set the video or audio as QoS, you'd OD the CPU in the switch. So what you want to set for QoS is the most important thing, which in this case is PTP. If you look at the graph here, the PTP is getting moved because of the audio and video, and just because of the random output that the switch has as far as its decision making on which packets come out first. So PTP has been spaced way back. But if you apply QoS to PTP, it's going to now have priority over the video and audio, and it will be able to be placed exactly where it needs to be. The 4610 uses that differentiated service code point 46, which sets the PTP as the highest priority going through that switch, so that you don't have that issue.
So, Steve, SMPTE 2110 standard specifies real-time RTP-based transport of uncompressed active video essence over IP networks. So if my understanding is correct, unlike SDI video, 2110-20 results in both a vertical and horizontal phase offset?
That's absolutely correct, Kevin. So the thing that we need to look at is, where is PTP relationship to black, but then where is the active video relationship to PTP and black? So PTP starts typically at the same exact point where black starts. It's going to be at line 0, pixel 0, all the way up the top of the VANC. So you have the ability to look at, where is my PTP relative to my black and burst, and it should be almost 0 by 0. Now there's always going to be a fractional horizontal offset, but it should start on line 0 and be really, really close to starting exactly where black and burst starts. So we can see that in the graph here. Now, the other thing we talked about is that normally the video then is going to start way later, like you said, offset from horizontal, offset from vertical. So the actual first pixel of the active video starts 21 lines later for 1080i or 42 lines later for 1080p. We really want the video to be in lockstep with SDI because, let's face it, in this world, you're going to have some SDI floating around, and for most of us, there's going to be a lot of SDI. And 2110 is what we're moving into, but it's going to be a slow progression moving in there. So we want to make sure that, just like aligning cameras or any other source, that the two are actually linked to each other. So we can actually measure based on, in this case, it's 1080i 5990.
So Steve, earlier in this webinar, you described the best master clock algorithm and how it ensures a resilient PTP reference. What happens to the PTP reference if the GPS reference source is unreliable?
It's a great question, Kevin. And this can happen a lot, especially with people with trucks going out to a venue, because in some cases, the trucks end up underneath of the stadium or underneath some other awning where you can't get GPS. So in a normal condition would be exactly like what we show here. You'd be looking at a perfect lock, lots of satellites, really good signal level. You'd be clock class 6, but when you can't get or you have unreliable GPS, it's going to fall out of lock and it's going to go into a stay in sync mode, and your primary generator is going to go to a clock class 7. Then if the second generator has a better clock class, it's going to walk over to it, but eventually it's going to fail because of the GPS being flaky, and you're going to get this toggle back and forth, and you definitely don't want that during any type of live programming. So one of the things that we need to think about in this design here is when we lose GPS, there needs to be a link, especially for trucks, between the two generators to be able to provide sync and lock the two generators, because normally they'd be locked to GPS. Well, when that GPS goes away, both of them are going to go into free run. And the last thing you want is the two PTP sources in free run and not absolutely phased with each other, counting time down in the microsecond, nanosecond range. So we need to add something to lock these. So if you use PAL Blackburst with VITSI on it, you'll take the time source from, in this case, the blue 4610, and you'll lock the red LT4610, and those two generators will now be absolutely perfectly in lockstep when when GPS is actually lost. So now the BMCA works, but one of the unique things here is going to be looking at how we set all of this up. So looking at this from another perspective here, we've got our satellite comes in, we've gone through the power up start, we do the listening, we do the BMCA, and it goes back and forth between these two units like we looked earlier. And we've added the clock class here. So if you look at the clock class on the unit on the right, his priority 2 is set to 1. So he becomes the Grand Master, and it is taking over. But going through this, if he loses GPS, it's not a big deal because the second generator has GPS. We're going to go through the same, they're still looking at the announce messages, and the unit now will start swapping announce messages, and the unit on the left now, since he has a better clock class, is going to take over, and everybody is fine. The problem exists when both units, or you have no GPS available, or you get flaky GPS that's walking in and out, then you're going to get that situation where the two can't talk to each other. And here you're going to have both of them set up. It's going to go back to the first unit on the right, but how long has he been out? And he's going to be the Grand Master, and it's going to go back to that unit because of priority 1, since they're both clock class 7. So we get into a unique situation here where, you know, the whole 1588 was designed around both units being locked to a good sync source. So without GPS in both of them, they're no longer linked together. So we need to look at this and come up with a way to actually lock these two units together. Well, so in our outside broadcast setting, this could be a challenge to always have GPS. So we can lock the two together with PAL and VITSI. Now you will have to probably set a preset and go in and say, okay, go to the second setup, you know, especially if you're going into a iffy situation, you want to start this and not try to rely on GPS that's flaky. And then lock the two units together. Well, so since the unit on the right is the Grand Master, he's going to be sending black with VITSI on it so that we have a time-based lock on the unit on the left. But he's going to be on an internal oscillator, so he's going to be clock class 248. And the unit on the left, since he's locking to what it thinks is a better clock than internal fractionally, he's going to be clock class 220. So he's going to end up being the Grand Master in this situation, even though he's locking off the unit on the right. BMCA will still work if the unit on the left completely fails. It will lock back to the unit on the right. So BMCA still works in this situation. It's just a little unique. The best way, as we see from the previous, would be to take and have a master lock source that is your clock coming from GPS, or you have this situation, and lock a third generator and then provide PTP from that generator down to the two generators on the bottom. That PTP passes the equivalent of GPS to the bottom two generators. So they're going to look like, from a clock class quality, that they are GPS locked. Now I can do the BMCA on those two units on the bottom. And even if I lose my clock or GPS on the top unit, he's still going to go into clock class 248, but he's still going to be sending PTP down to the two units at the bottom, so they're going to still have a stable clock coming into them. The unit on the top is in holdover, so he's still running on that clock, but the two units get exactly the same data, and now the BMCA between those two clocks is completely unaffected in this particular situation.
So just to clarify here, Steve, the third LT4610 that's been added to this, the master clock, is not part of the best master clock algorithm. It's not being polled, it can't be selected as the grandmaster. Is that correct?
That is absolutely correct. If you look at the domains, it's a different domain feeding the two units down below, and then their output will be on the domain that will be your truck's domain. The domain out of the first one is just the domain to lock the two units, and it's not part of that BMCA polling, but it just gives the same stable clock to both units so that it's the equivalent of GPS lock from the BMCA. It will work between the two units as expected. And this even works with a flaky GPS, and it doesn't ripple down through the system like each unit being locked and one unit falling out of GPS first than the other unit, or both units coming in and out of GPS. So it's a much better way to do it.
Right, Steve, I think we're probably at the point. We've just run slightly longer. Well, should we throw it open to the audience and let's see where they take us?
Yes, we've received some really great questions during the presentation. How many follower devices can be connected to a grandmaster, and how do you calculate how many?
Yeah, the calculation could be fun, but typically, mathematically, it's just under 1,000. But realistically, on a normal SPG, you can do about 800. Boundary clocks typically are about half of that amount, just because there's so many, because each port ends up being a boundary clock, and there's a lot of CPU time being absorbed in a boundary clock.
I think you also have to be careful looking at the frequency of the announcements, because that can affect it as well quite significantly.
Yes. Yeah, you really don't want to take the announce messages and sync messages and run them up past what the SMPTE recommendations are.
I mean, lots of architectures we see is the PTP generator is connected into a boundary clock, and then it starts to fan out from there. Because, you know, in a sizable IP network, you could be talking thousands, tens of thousands of nodes eventually if everything's connected.
Yep.
And you want to build that architecture so that you don't overload. Like you do with the video traffic, when we talk about 2110 and the timing and all of that, you've got to put the same thought into your PTP network, and you don't want, as Steve just showed you there, to build bottlenecks where the messages are going quicker out than they're coming back, because it's a recipe for disaster.
How would you suggest we lock two grandmaster clocks in lockstep if there is no GPS signal available? And then second part of that question is, how can we guarantee the baseband sync coming from each grandmaster without GPS will fail over hitless in the ACO?
Without GPS, you're going to be in a clock class 248. And what you want to do is take the primary generator, lock the second generator to the primary generator, and you'll typically either have it PTP locked to the primary generator to your grandmaster, or you can use Blackburst. And as I said in the other, it's best to actually use a integer value Blackburst, i.e. 50 hertz, because there's no jam syncs in the messages because it is integer based. One of the problems with 5994, 2398 is we have jam syncs in our Blackburst messages, and you got to deal with the jam syncs. And so if you use 50 hertz, you don't have jam sync. So you have to lock the two generators together with either Black or PTP. And so you have to pick one that's going to be your grandmaster. It's going to lock the second unit so they're both in time with each other. And then they will both be clock class 248, but at least they'll be in time with each other.
Here's an interesting one. You said the clock names have been changed to leader and follower. Who changed these? Was it SMPTE or IEEE?
It was a little bit of everybody. I think part of it came out of AmLaw, part of it came out of IEEE, just being politically correct, if you will, instead of the old thing where it was slave and master and then grandmaster. So it's just trying to be PC.
So, Kristen, I think we had one question actually came in before the event.
Yes, we sure do. It starts with a comment. It'll be interesting to describe how to monitor the relationship of the encapsulated sources from SDI to IP to the reference. Synchronization on 2110 is very important. It's important how to discover a source that's been encapsulated to 2110 but not locked to the same reference, or maybe not locked. The signal seems good, but it should create an AV timing delay. In this case, it's nice to find synchronization issues using the LV5600. How will PTP timestamp the video as well as audio stream?
So every packet that's created gets an RTP timestamp that is the epoch value. So we know exactly, so when we create a frame, that entire frame gets the epoch value of the first packet. So every packet within that frame, we know who it belongs to because they will all be the same epoch value in that RTP timestamp. PTP itself is going to lock itself typically at the same point, like I'm showing on the chart here, that up here, pixel 0, line 0, which is the start of black, will be the start of PTP. Then, so you can look at your PTP and say, okay, is my PTP referenced to whatever my NTSC source is? And it's really easy if they're both coming off the same generator. They're off the same clock. But at least you can tell what the clock offset is when you look at that. And you can look at the lock source, and here you can see that it's exactly locked. Now, for the question about where is my video locked, the active video is going to start, since 2110 only sends a screen portion, i.e. the active video. If it's 1080i, it's going to start 21 lines after the start of PTP, or if it's 1080p, it's going to start 42 lines later. So one of the things that you want to look at is, for the video I have, in this case 1080i, I should be 21 lines out, and my horizontal here is 21 lines off, or excuse me, my vertical is 21 lines off coming down, and it's a little horizontal off, but that's normal that we have, a box around this that we need to stay within. Now, so this is a reference to PTP. If I walk over to my generator really quick here, I can look at my sync source that I am locked to. And so this is actually live. So you can see I am 21 lines out. And if you are looking at PTP as my reference, and I'm looking at those RTP timestamps, that RTP timestamp is 21 lines late. If it is not synced, you will get a ping pong bounce of this value going across. And I'm not sure how well this will show within the confines of Zoom, but that is what it'll look like. And the values will be changing all over the place, or will be a set offset. If they're synced but not in time with each other, you will see the change here. And this is in the case of a free running source that is not synced going into a 2110 network, which you don't want to have. I got a little frame sync involved here, so my video source is actually free running, and I go through a little frame sync, and I can realign these guys back where they belong here. My frame sync happened to come up 180 out. See if we can get him to come up where he belongs. And okay, it came in at 20 lines this time, which is still fine. You got a couple line variants plus or minus, but you can see the horizontal is almost ready to kick over to line 21. So I'm within the lock window of almost all devices that would be in my system.
So basically having a device like the 56 or 76 that can connect to both black and burst and PTP reference gives you that flexibility to chop and change and track
Yes.
down where your video is actually referenced and what it's not referenced to. One more question I'd like to throw out there, Steve. It's, what is the security method used for PTP so it isn't vulnerable to something like a DNS attack?
Well, normally your PTP network is completely isolated, never hits the world. It never is anything within your engineering network. PTP is normally a confined network in and of itself, and it doesn't leave your facility. So an attack of the PTP network itself is not easy. The powers that be within the standards groups are working on how to implement some of the security measures that we use within the IP communities, but none of those have completely been ironed out yet, and there's still a lot of talk about that. But in 99% of the cases, it's a completely self-contained network that is not connected to any other network within your facility, and getting it hacked or anything else is next to impossible. Yes?
Any final thoughts on how to unite SDI and IP in one system?
Biggest thought, at least that I have, is get yourself to where your SPG that you have going into your ECOs are the units that are providing your PTP. That way, there is never a question of part of my house being locked to this reference, part of my house being locked to this reference. The black and burst is coming off of the same clock that is creating your PTP. They are 100% locked. You may have to start out, like that first drawing I said, where your PTP SPG is locked to black and burst inside your facility until you get to a point that you can recreate your sync source within your facility and have your PTP and your black all coming off the same sync source and hopefully locked to GPS. It is critical to have them locked to GPS.
Any questions we didn't get to today, Steve and Kevin will be in touch with you personally to answer them. We want to thank all of you for attending. We hope you found this seminar as interesting and informative as we did putting it together for you. And we want you to know that this will be posted, the entire video will be posted on the Leader YouTube channels, and we'll also produce an audio podcast episode very shortly. For any of you who would like a copy of the presentation today, along with the transcript, please watch your email inbox and you'll receive links to download these materials.